Okay, welcome. Welcome to the second part of MEADMAT. And now we will be talking about numerical methods, right? So for this time around, right, it'd be very helpful if you guys have a laptop open with you so that you can experiment along with me as to how we're going to be able to achieve answers using numerical methods instead, right? Last time we talked about analytical methods in general, right? We were talking about a recap of differential equations, right? We were talking about how linear algebra can help us get answers to more how should I say this, more um organized, in a more organized fashion, right? Answers to different linear equations, differential equations, linear differential equations, stuff like that. And now we will be talking about numerical methods for when you don't want to think, right? This first part of the second part right here, so basically topic 3, we'll talk about numerical methods for solving different equations, right? We're for getting roots of different equations. And the last part, topic 4, will be for getting numerical solutions to differential equations, right? So these are parallels of each other, right? So for topic 3, we will begin with numerical methods, basically root finding methods, and it will be split into 3 parts. Our first part will be bracketing methods, second part will be open methods, and third part will be the Newton-Raphson method, right? Which is the big boy, the start of the show, right? But the thing about this is we will now begin with bracketing methods, and the bracketing methods, both of them their foundation is rooted in what we call the intermediate value theorem, right? The intermediate value theorem states that if a continuous function f of x exists such that this value of s is between an f of a and an f of b, what that basically means is that you've already substituted value of a into this equation and a value of b into this function pala na equation. If you've substituted those values already, right, and there is a value between them, say for example we call that s, for some interval which is the interval of those two values a and b, then there exists a number c inside that interval such that the f of c is equal to that same value which is in the middle, s. So you might say, huh? I don't get that, right? Okay, so what I'm going to do here is explain it visually instead of mathematically or legally. Seems like we have a lot of terms in here. Say for example, this is your function s, right? This is your this is your function f of x. And say for example, we're going to substitute a value of a. What happens is that if you substitute a value of a, right, what we will compute is an f of a, which is right here, right? Which is right here. This is the y coordinate of that point, right? So that is now your f of a. Now, say for example, we have another one here, b, right? And when we compute that, when we put that into the function, we will get the y coordinate of this function, which is f of b. Now, say for example, now we have a value s somewhere in there, somewhere in the middle of f of a and f of b. That means that there has to be a point between a and b, right? There has to be a point between a and b wherein if you're going to substitute that point, it will result in an s. So in this case, this is now your magic value. This is the value that you want, which is your c, right? And so you might say to that, oh well, it only works for this version of the function. What if we have another function? Well, let's test it out. And the thing is, uh how am I going to say this? Right? This will be true for all continuous functions, okay? For all continuous functions, this will be true. And well, let's try another one. Let's try something that looks a little bit more funky, right? Maybe something like this, right? Say, for example, something like that, right? This is your f of x. And from what we see here, your a will intersect and be here, right? Be here, f of a, and then your b will be somewhere in here, right? Which is now f of b is somewhere here, right? F of b is somewhere here. Say for example, we have c is here. Oops. For example, c is here, Oh, sorry, your S is here. If you track that there, oh, congratulations, there is an intermediate value, right? So you might say, well, it just so happened to work again. What if, I don't know, say for example, your B is here, right? Say for example, your B is here. Okay. Okay. So if that is between f of A and f of B, well, what's supposed to happen now is there needs to be somewhere between f of A and f of B. For example, maybe the S is now here, right? There you go. It will still work, right? It's still between A and B. Okay. So you might say, oh, well, what about this one, right? What about this part right here? What if we're going to have something like this? Let me just reset this this drawing. Say for example, we have a simple parabola, right? Say for example, I get A in here, and then I get B in here, right? And it just so happens that both of them are the same value, right? F of A is equal to f of B. Well, in that case, this theorem is not going to help you with anything, right? Because the thing about the theorem is that it only accounts for values within this very different range of f of A and f of B, right? It does not say anything about the possibility that f of A is equal to f of B, right? So in this case, well, the intermediate value theorem is not going to help us, right? However, say for example, if your B is somewhere in here, right, you might say to yourself now, well, right, in this case, how am I going to say this? This is still going to work, right? Say for example, your S is here because now your f of B is somewhere just a little bit above, right? Your S will hit this and will now get to a value of C. Now, why does this work, or rather, why is this the foundation of our bracketing methods right here? Well, bracketing methods, from their name, have a bracket, right? Have a bracket wherein, say for example, you have a lower value and an upper value. Let's call that A and B. What's going to happen is that you for sure know the solution is going to be between A and B, right? So in this case, the bisection method works like this, right? Based on the name, a bisection method, what it does is that it methodically cuts the range of A and B in half every single time until you get to a close enough range wherein you can say, you know what, what do you call this? The value of your answer, or rather the root, is going to be somewhere in between them. Okay. So what you're going to do is this: you're going to have your function right here, or you're going to have your equation, and you know what? Let's already start with number one right here. X cubed minus x minus 1 is equal to 0. And then what they're saying to us currently is we're going to have to try between 1 and 2, right? What we're going to do is something like this. How do we even know how to bracket, right? The thing is, bracketing is a little bit easy, but it's going to be a little bit tedious if you don't know really where the where the general range of the root is. What's going to happen is something like this. You first substitute values for your function until you get two values wherein one value is positive or greater than 0, and one value is negative or less than 0. And so now let's think about it in terms of the intermediate value theorem. Say for example here, you have one value A. So let's say for example we have here A, wherein the what do you call this? Wherein the value of f of A is positive. So say for example f of A is positive like this, and then say for example in here we have B, and the value of f of B is something that is negative. So f of B is less than 0. In this case it's somewhere here. So your red point is here and your blue point is here. Because we don't know the shape of the graph. I mean, even if we do know the shape of the graph, the thing about it is that we really don't know about the behavior of your function. All that we know is that there is going to be a solution between them. Why do we know that? Because the intermediate value theorem states that if you have an interval A and B, and if you have this interval f of A and f of B, right, since f of a is positive and f of b is negative, something that you know should be between them is 0. And so even if we don't know where it is, there's bound to be a point wherein it will cross 0. That is how we know that our root is somewhere between the bracket of a and b. Because a has a positive result if you plug it into the function, and b has a negative result, or vice versa, what you know at the very least is that somewhere in there, somewhere between the bracket of a and b, is your answer. Okay, so that's how it's going to work. Okay, so now let's try and implement this using not only what do you call this? Not only Desmos, right? We'll have Desmos here with us, but we'll also have Excel, right? Excel is the main weapon for quiz 2, and when you are going to be taking quiz 2 in week 13, you will have to have Excel open, and every time you have a result, you must submit also your spreadsheet, so that we just know, or rather I would know when I'm checking your paper or when I'm checking your submission, that you really did do it, right? So it doesn't matter if it looks a little bit ugly, that's fine. Okay, so now what we will do is we will just plug into here, right? X cubed, right? F of x is equal to x cubed minus x minus 1. So we can see in here that indeed the answer is going to lie somewhere between 1 and 2. Notice that this is your x equals 1 and this is your x equals 2. Let's clean up a little bit. Clean up a little bit. There you go. Make these smaller. There it is. Right? Your function is here and your root is going to be wherever this is. So our current root in here is 1.32472. What we're going to do is we're going to recognize and first start with the fact that, okay, if you substitute f of 1, right? If you're going to substitute f of 1, let's just try and do this here. F of 1 is just going to be 1 cubed minus 1 minus 1. So that will be cancel negative 1. On the other hand, your f of 2 in here is going to be 2 cubed minus 2 minus 1. So that's going to be 8 minus 2 minus 1. That is 5. Note that because one of these is negative and one of these is positive, we can now start our bracketing method. Right? Our bracketing method will proceed as follows. Now that you have checked, okay, one is positive, one is negative, what you're going to do is get the new value at the middle of A and B. This is why it's called bisection. Right? So literally, what we're going to do is just average, right? And we'll keep averaging until we get a satisfying answer, a satisfactory answer. So now, our next will be, right? Our next m for midpoint in here, is just going to be 1 plus 2 over 2, which of course is going to be 1.5. So what we will do with the 1.5 now is that we'll just substitute, right? So let me make this, I don't know, blue. Let me make this blue. And now what you will see is that that blue portion, if you're going to substitute it into the value, into the function rather, your 1.5, f of 1.5 is going to be 1.5 cubed minus 1.5 minus 1. I don't have the mental math capabilities to substitute this. You know what? Maybe I can. This is 3 halves, right? So this is 3 cubed over 2 cubed minus 3 over 2 minus 1. So that's going to be 27 over 8 minus 3 halves minus 1. Let's turn all of that into 8, right? So this is going to be multiplied by 4. This is 12 divided by 8. This is 8 divided by 8. 27 minus 12, that is 15 minus 8. That is 7 over 8, which is 0.875. There it is, right? And now you say to yourself, that's positive. Now the choice is going to be this. You remember your what do you call this? You remember your initial guess on the left side and the right side, right? The lower bound and the upper bound. Now, because you know that this new midpoint right here, this new point that you've created is still positive if you're going to substitute it into the formula, into the function rather. Now, the question is, what will you replace? So, of course, if you replace the lower bound Well, both of these values are now going to be positive, right? Both your f of a and f of b are now going to be positive. So now that's not going to guarantee that the root is somewhere in there. Therefore, if it's positive, you replace the positive. If it's negative, you replace the negative. So this is what's supposed to happen, right? You get f of m, and if f of m is positive, replace what was positive. In this case, f of a is equal to is greater than 0, or in this case f of a is positive, so you replace a with the new value of m. If your f of m is negative, follow which one is negative and then replace that instead, right? And the thing about this is that if you're going to search for the bisection method on the internet, the instructions will be a little bit different, and because those that's because those instructions are better for algorithms, right? Of course, I'll teach you guys the algorithm for later, but for now, right, this is what we'll do, and we repeat until this is epsilon r is reached. In this case, this is what we call the approximate error, relative approximate error. Thing is, I don't know the real value of this root. I can only get approximations to the root. And the thing about this is that now we are operating under the assumption that if we're getting closer and closer, right, our errors or our approximations should be smaller and smaller. Right? Our approximations should become smaller and smaller, or rather, the changes within those approximations are going to get smaller and smaller. What do I mean? In this case, right, we still don't know anything about the real answer, right? It's 1.32472, but currently we are just under the assumption, right, that it's between 1 and 1.5. That's everything we know. However, right, that's going to change once we go and do this a little bit more, sabihin na natin, a few more times, right? So let's repeat this. Right? Let's repeat this. We will now have the midpoint between 1 and 1.5, which is 1.25. Now you will have that, and then you will say, okay, if you substitute 1.25, you will get a negative number. I don't even care about the number itself. I just care that it is negative. So now what we will do is you will think, okay, 1 gives you a negative number and 1.5 gives you a positive number. Therefore, I will replace 1. Right? And now we notice, wait a second, now the bracket is getting smaller and smaller. And so now this is now our this is now our, what do you call this, our relative approximate error. This basically is the length of that bracket, right? This basically is the length of that bracket. We need our answer to be, right, sure, between 0.0001. So say, for example, our answer is going to be 1.24356, right? Our bracket needs to, at the very least, be between, or rather, our bracket, the thing here, must be bound by at least 0.001. So in this case, say, for example, if your bracket is 1.2435 and 1.2436, that is 0.0001 away from each other, and we will stop here because we're like, okay, this is close enough, right? This is accurate enough for what we want to do. So that is our goal, right? That is for the bisection method. We will keep going. Currently, our bracket in here is 0.25. It's gonna take a really long time for us to do this, right? So I'm just gonna continue doing this, right? Currently, it is our, what is this? First, second, third, right? This is now our third attempt, or rather our third attempt. We will now take the average between 1.25 and then 1.5. We will get 1.375. And now, if you plug in 1.375, you will get a positive number. So you will replace 1.5. And we will continue doing this again and again. Okay? Now, we will take the average between 1.25 and 1.375. 1.25, 1.375 divided by 2. And now that gives us 1.3125, which gives us a negative number. So what we will do is we will bound it between 1.3125 and 1.375, and then we repeat, so on and so forth. You will see that yeah, this does become a little bit tedious, and that is why I don't want you guys to do this on paper, right? This is just too much, right? If right you go to 1.34375, you'll get closer, and this will become a positive number. That means that you will now replace 1.375, and you will see that it just gets closer and closer and closer to the number. The thing about this now is, now you might say, okay, it seems that right, at the first 2 points, right, at the first 2 points, your bracket is A minus B, right? And at the second try, right, at the third point, what you will have is A plus B over 2, or A minus B over 2, or B minus A pala over 2, right? In this case, we are assuming that your B is higher. But in this case, what happens is that for every iteration, the bracket is halved. It's halved and it's halved and it's halved, right? So this is what happens, right? At the first bracket, or rather at the first iteration, so we have points, right? Points. We have 2 points, which makes the first bracket, right? Your range, let's just say the range, the bracketing range. Let's say, for example, that is L. Let's just B minus A or A minus B, or you know what? Let's just have an absolute value in there so we can always say that it is positive, right? If you add another point, what you're basically doing is that you are halving the range. Add another point and you are halving the range again, right? That is what we are, that is what we have been doing in here. When you had 2 points, the range was 1. When you had 3 points, the range was half. When you had 4 points, the range was 1/4. If you have 5 points, the range is divide by 8, so on and so forth. And now you will see a kind of a what do you call this? A kind of a pattern pop up. Note that in this case, however many points you have, n will determine your range, right? Your range. So in this case, if you have n points, that corresponds to an L divided by what is this? 2 raised to n minus 2. Right? Okay. There you go. And you might say, okay, so say for example, I am going to have 3 over, sorry, say for example, this is 5 now. 5 minus 2 is 3. So now your L is L divided by 2 raised to 5 minus 2, which is 2 raised to 3. That's now L over 8. Now, this is going to be your formula for your epsilon r. This is now your length of bracket. Right? So say, for example, we know the length of our bracket in here is going to be 0.0001. Let's take our original range. What was our original range in the first place? Our original range was 1 and 2. So that means that that is going to be 1 all over 2 raised to n minus 2. So in this case, you will have 2 raised to n minus 2 is equal to 1 over 0.0001. So that is 10 raised to negative 4. And so if you put that in the denominator, what you will get is basically 10,000. 10 raised to 4. And now what you can do is count, at the very least, how many iterations you need, how many points you need to get this answer. How are we going to do this? Well, your n is somewhere on top. So what we should do is put an ln. What an ln does, if you don't remember, right? An ln is has superpower, wherein if you have an ln of a raised to b, what you can do is put that b downstairs. What I mean is b and a. So in this case, now you can do n minus 2. What is this? Ln 2 is equal to ln of 10 raised to 4, or 4 ln 10. And now what you can do is divide both sides by ln 2. We will now have ln 2 in here, and then it's n minus 2, so it's going to be n is equal to 2 plus 4 ln 10 over ln 2. Let's put that in our calculator right here. 2 plus 4 ln 10 divided by ln2. That is now 15.2877, or what is this going to be? 16. You need 16 points, right? 16 points for you to be able to get to a value of 0.0001 bracket. And that is if your range is 1. If your range is 2, right? If your range is 2, then well, it's going to take 17 points because you're going to have one more time. Okay? And so what we will do now is we will go to Excel and basically try this out. See what we can do. See what we can do. All right. Let's have a blank workbook right here. Let's zoom in so that you guys can see stuff. Okay. Currently, my what do you call this? My font is very ugly. Let's try changing this. Courier. JetBrains can work. Yeah. Okay, let's just go with JetBrains. Okay. So what we will have here, I will just write down my f of x so that I don't lose track of what it is. Oops. Don't lose track of what it is. I'm going to... Di ba pwede yun? Okay, how do you align right? I forgot. Margin center. This is going to be x cubed minus x minus 1. Right? And we're going to stop in here whenever we see that this is going to be 0. Do you superscript? I mean, I guess I superscripted it like that, but okay. What we will now do in here is iteration or maybe point, right? And what we will have is point ID, basically. This is point ID, so 1, 2, 3, and then so on and so forth. Let's just drag this down. We have 20. Say, for example, we have 20 iterations here, just so we can rest at ease a little bit, right? Point, and then let's make this a little bit smaller. And then now what we will have is x, and then your f of x is. And so what we will have in here, what we just want to test out in here, let's make everything. What we want to do is 1 and then 2. That's going to be our 2 points right here. Or you know what? Let's just make that guess. Guess, and then guess. Then this is point 1, 2, 3, so on and so forth. Let's just have it like that. And your f of x for here will be this raised to 3 minus c5 minus 1. Okay, so currently it's -1, and then this is 5. So we have everything correctly naman. Those are our 2 guesses, which means if you guys want to have some validation here, that's completely fine. Valid? Question mark. How will we know that this is valid, right? This is going to be valid if one of them is positive and the other is negative. You might say to yourself, okay, so how are we going to do something like that? Well, if you think about it, right, we don't want anything that is both positive or both negative. In this case, what we can do is if we multiply these values, they should be negative. Right? It's fine if this is positive and this is negative, so long as we have something that is different, right? So what's going to happen is that I will have this merging center right here, but I will merging center this, and what I will say is that if a condition is met, what we'll do is say that okay, we can go on ahead, right? So if this times this is less than 0, right? That means it's negative. So that means value is true, value of true, valid. And then in this case, maybe something like not try again. Okay. Something like this. Okay. So say for example, we have 0. Okay. 0, -1, negative. Really? What is that? I mean, I guess it works. -2. Okay, yeah, never mind. 1.5. There it is. It's gonna say try again. Okay, there you go. Let's just have this a little bit smaller. I'm so sorry. I feel like I'm being a bit too... All right, there you go. So we just have it at 1 and 2. It's valid now. So what we can do now is we can try and, you know what? Let's just make it iteration. Iteration. And then we will have here x. We'll have here f of x. And then we will have here our, what is this going to be? Epsilon. So this is epsilon r. Epsilon. I don't know. Is there an insert? I mean, you can insert a symbol. Let's find epsilon. There it is. Okay. Then r. It's happening. That is way too large. Is it 12? Okay, whatever. Then let's have this superscripted. Sorry, subscript. There you go. Okay, that's good enough, I think. Okay. All right. What we will do now is that we will create basically the f of x. Sorry, the m in here. So we will do average of 1 and 2. C5 and C6. Okay. So we'll create this, and then what we will do is do this again, divided by raised to 3 minus C9 minus 1. And let's just drag this down. Okay. And let's just drag that down, and we will see, we will continue to understand what's supposed to happen in here, right? How will we choose the next value of our iteration in here? Well, we're going to do now is that we will set up an if statement, right? We will set up an if statement such that if this is going to be positive, you will replace the positive number. If this is going to be the negative, replace it with the negative number. The thing about this is that we humans can think, right? Think as in, oh, this matches with this, therefore this replace, blah, blah, blah. The thing is, computers can't do the same thing, right? They can't just take in like implicit assumptions and then spit out, okay, this is how it's supposed to be. We need to be very precise with how we're going to do this. And what we're going to do with this is we're going to apply the same kind of logic that we were seeing earlier. If both of them, right? If both of them result in a if they are opposite from one another, right? Their products should be negative, right? If one is positive, the other is negative, their product is negative. It does not matter about the order. If it's positive first, then negative next, it does not matter, right? So in this case, how are we going to do the whole replacement thing? Right? The whole replacement thing, what we will basically do is just try and understand now, right, what's going to happen. Okay, let's think about this. Let's think about it this way, right? What we will do is play around with the products of the values of f of x. Notice in here that your f of x is positive. Therefore, what we want here to appear is the value, which is the average, and then the, what do you call this? The average, and then the lower value, your x equals 1, right? So from this case, we can now think, okay, if, right? And we will have to do with the product of something right here. So if, say for example, the product of this and this is going to be less than 0, that is true, right? That is true. So what we will do now is that we will create, right? We will create the average of, right? What values? We will create the average of the value of, well, this is going to replace the x equals 2, right? So we will create the average of this and this, right? C5 and C9. On the other hand, if that is not true, we will then use the average of, right, C6 and C9. Is this 9? Let me just type it then. Okay, there it is. And now what we can do for now is just drag it down, see what's going to happen. Yeah, we're going to break it. And so the what is the reason now? Well, what we're going to have to think now is, well, when we were dragging this down, the values of 5, 9, 5, 9, 5, 9, 5, 6, and 9, those values were getting dragged down along with it. So now instead of 5, 6, and 9, this is going to be 6, 7, and 10. Right? So we need to have a little bit of a change how we're supposed to handle something like that. Right? Okay. So how are we going to do something like this? In this case, very clearly, this is already wrong. Right? Your 1.625 is already wrong because now you're looking at the value here between D6 and D10. Right? What you're supposed to do is you're supposed to look at the value of the previous, right? The previous iteration and the next iteration. So maybe what we would do in here is have a little value that is better for iteration levels. Right? One wherein you can write down and just copy the lower bound, and one where you can write down the upper bound. So maybe this is not the way forward. Let's try and change this up a little bit. Right? Try and change this up a little bit. What we will do is now have x and then L and then f of xl, right? That is the lower bound. And then here we have xu and then f of xu. Okay? And note that we will have in here is a range, right? We can now compute for the range by itself. And then what we will get in here is x of m, right? xm, and we will get fxm so that we can now find, okay, this is what's supposed to happen. Okay, let's fill in all of these values. We will have x of L, and here, whichever one is lower, right? Whichever one is lower, that's fine by us. Going to be 1, then it's going to be this one, d of 5. This one is going to be c6. This one is going to be d6, and our range in here is just going to be xu minus xl. So absolute value in here we'll have xu minus xl. I mean, if you want, there's a whole like lookup thing in here that you can do, but whatever. Right? xm will be the average of these two values. Average of these two values, xl and then xu. So what we'll create is 1.5 and then just fxm. So what we will do is this is the 3 minus like h9 minus 1. You will have something like this. And so let me just try and see if I can make these guys have bigger values or have bigger, what do you call that? Have bigger decimal places. What we'll have here is do this. Why don't they increase? Increase decimal place. 7, 8. Okay, 8. So wait. So, oh, you want them to be just numbers. Okay, fine. What is this? 7, 8. Here you go. Okay. I know this sounds a bit overkill, but whatever. What we will do here now is make the computer understand that we need to replace xm with xu, right? We need to replace xu with xm pala rather, right? So in this case, what we will do now is have a little bit of logic in here, right? So xl, what will happen if the fxl times fxm is going to be negative? Well, in this case, because they do not match, right? Because they do not match, what will happen is that it will retain itself, right? It will retain its own value. If the values of this, if the product of these values are going to be less than 0, it will retain itself, right? However, if they are not, if they are positive because they are the same sign, you'll now take the value of xm. So if this is correct, what I should get is still 1, right? And I should still copy that value. You know what? Let's make this a little bit more make this a little bit more robust. Minus C9 1. Then this should be is this E9, but rather E9 raised to 3 minus E9 minus 1. Here we go. Then C6. Well, that doesn't matter. What we're going to do here now is set the same condition, right? This times this is less than 0. In this case, this is now untrue, right? This is now untrue. So what's going to happen is you're going to switch, right? You're going to switch. In this case, if this is true, you will retain. If this is untrue, you will switch. So we should see it switching, right? I will drag this down as well. There you go. And then let's extend these guys a little bit. And then the range is going to be, actually, we can drag this down as well. There it is. And now the XM is going to, we can drag this down as well. Drag, okay? Then drag this down as well. And now, actually, we can drag this down. And this down as well. You can now see that the range gets smaller and smaller and smaller and smaller until, right, you will see 0.0001, right? Okay. Now you will see in here your f of xm as well gets closer and closer to 0, right? Look at this, right? At what is this? At iteration 18, it's already, what is this? It's approaching 1 times 10 raised to negative 6, which is pretty great. I mean, like, it's not great considering the other methods that are going to come after, but this is our bisection method, right? This is our bisection method. Okay? So if you guys have questions about this, let me know. But this is how we're going to have our bracketing methods, right? In our bracketing methods, the best way forward would be to consider iterations itself, right? Not just the points themselves, but the iteration. And now, maybe what would be better is if we replaced our formula in here. Instead of points, we now think of iterations, right? So iterations, we have our first iteration, and our range in here is our normal range, our L. And then if we have 2, we have L divided by 2. If you have 3, we have L divided by 2 squared. If you have 4, we have L divided by 2 raised to 3, so on and so forth. And so if you have n iterations, that means a range, or your range, should now be L raised to 2n minus 1. L divided by 2 raised to n minus 1, which should serve as your epsilon r, your approximate error. So in this case, if you want to know, right, if you want to know your approximate error, or how many iterations it would take you to get to that approximate error, let's now try and back solve for n. In this case, we will take this, right? We will take this, and then we will switch sides in here between e of r, epsilon r, and then 2 raised to n minus 1. We'll have is L divided by e r, and then you will have in here 2 raised to n minus 1. What you can do in here is have both sides be included in an ln, and what you will have is ln of L over e r, epsilon r, and you will have in here n minus 1 times ln 2. What you're basically doing in here as well, what you can do with this is you can turn this into, right, if you have an ln of a over b, you can turn it into is ln of a minus ln of b. Okay, so you can have in here is ln of L, right, your original range, minus your ln of e epsilon r, and then you divide both sides by ln 2, you will get this. Now this is your n minus 1. So you put you put the negative 1 to the other side. You will now have the number of iterations is 1 plus ln of L minus ln of epsilon r all over ln 2. In this case, our original L was 2 minus 1, which is 1. So 1 plus ln of 1 minus ln of 0.0001 all over ln of 2. Actually, this is just 0. So what you can have is ln negative ln of 0.0001 divided by ln of 2. You will have 13.287, or maybe let's just take that to 14 iterations. Right? It will take us 14 iterations for us to get that value of 0.0001. And note that it indeed is true. There you go. So there you are. Okay. And now we will solve for a little bit more difficult kind of equation right here, sine of x. And when you are looking at a trigonometric function in the wild, always assume that your x is in radians. Okay? Degrees are a man-made thing. Radians are a ratio of the arc length divided by the radius. Okay, so that will always be true no matter where you are. And now they say we try 1, 3. Right? So we try 1, 3. Let's actually see what this looks like first in our equation right here. Sine x minus x over 2. So we see in here that if we're going to bracket this between 1 and 3, your answer is somewhere between your answer is somewhere 1.89549. Note that in this case, your 1 and your 3 have conflicting signs. So that means we are good for the bracketing stage, right? What we will do now is really, let's just try and copy this. Copy, move to end. Have here bisection method example 1, and then let's have here bisection method example 2. That sounds like bowel movement, which is very funny. Sine of x minus x of 2, let's just make that 0.5x. Okay, in this case, our guess in here is going to be 3, and well, change the whole thing. This is going to be sine of c5 minus 0.5 times c5. Then in this case, sine of c6 minus 0.5 times c6. There you go. It is valid. So what we will do is just change these things, right? Note that in this case, this is the only thing that changes, right? And all of the internal logic about choosing what value to put on next is going to be unchanged, right? This is going to be sine of e9 minus 0.5 times e9. Okay, and then we just drag this down. Note that your original range here is 2, so we just drag this down. And I forgot to change this as well. Going to be sine of, is this h9 minus 0.5 times h9. And now we drag this down as well. And there you go. Our answers keep getting closer and closer to 0. Okay? And in this case, instead of stopping at 14, right, it should stop at 15, iteration 15, because, well, our original range for the first one is going to be 1, and it took us 14, or technically 15 iterations for us to go below, right, to go below 0.0001, right? In this case now, it will take us another one, because you're gonna have to have the 2 first, right, for you to get 1, and then it will take you 15 iterations from then. So it is at iteration 16 where you can stop, right? It is at iteration 16 where you can now tell your your computer maybe that your answer is going to lie somewhere between these two values. Okay? Answer is going to lie between those two values. Right? So when we are discussing, or rather when I am going to look at your quiz 2 or maybe your final as well, right? What I need to see is this, right? I need to see this kind of thing crop up. Okay? All right. So now we move on to the next part of this, which is the regular falsi method. As you can see, it's a little bit more, what do you call this? It's a little bit more involved now, but the regular falsi method, it's also called the false position method. You will see, you'll understand that, oh, okay, that's what they do, right? What you're going to do is something like this. First, you do the same thing as the bisection method. You have a bracket, right, wherein at one point or one end of the bracket is going to be a positive and the other is going to be a negative result, or vice versa. Right? Once you have that, what you will do is that you will create a line between those 2 points. It is not anymore just I will take the half. The thing about taking the half is that, okay, that's a smart idea, but the thing about that is that, well, if you think about it, I feel like, or rather, you're going to get the feeling that, well, there's supposed to be a smarter way towards this, right? Note that in this case, it took us, what, 15 iterations for us to get to 0.0001 or below 0.0001. Now, what we will do for the regular falsi method is create a line. And now in this case, say for example, you have this curve right here, and you have the root somewhere in here. When you create a line, now look at the bracket that's going to create, right? Okay. Well, what's so powerful about this? Well, what you're going to do is wherever the line will touch the x-axis, that will be where your next m is. And the thing about this is that you don't have to do this every single time, right? You create the line and then you so on and so forth. What you can just follow is this formula right here. The derivation is here. What you're basically going to do is that, well, you will find the slope of the line first, which is just going to be rise over run, right? This thing. So y of b minus y of a, and then x of b minus x of a. So it's like this. Right? This thing, all of that is given. It does seem like it's very, how should I say this? It's very complicated, but in this case, well, all of those things are given. So there's no issue. Right? We said that this value m, this new value m, should touch the x-axis. That is why its y-coordinate is 0. So you substitute those values for x and y, and basically you back solve for m, back solve, you will get to here. Right? This is the heart of the regular falsi method. Right? And what you will do is, just like before, if it matches the sign, replace. If it matches the sign, replace. Right? And so with the same logic that we were looking at earlier, this is what we'll do using the regular falsi method. Instead of having this thing, which, for the lack of a better term, it's not smart. Right? It's not smart, it's just indiscriminate, right? It does not discriminate how big or how small your bracket is. What it will do is that it will just have it. No questions asked. In this case, depending on where the 2 endpoints are, it will give you a somewhat smarter, at the very least, a calculation, right? That is based on not only your values of a and b, but also the results of those values a and b, which is f of a and f of b. So now in this case, let's just try it out. What I will do first, right, is that I will highlight in here when it starts to become below 0.0001. So in this case, it's supposed to stop in here, right? Look at that range. That range means it's over. So technically, these things are no longer necessary, right? They are no longer necessary. Same for here. Notice that after this, right? after 16, iteration 16, they can all stop, right? Now, let's try and replace our XM in here using the regular falsy method, right? I will move to end, I will create a copy, and now this is now regular falsy example 0. I am taking the original in here, x cubed minus x minus 1, and instead of just doing the average, what we will do now is we will create this thing, a times f of b minus b times f of a all over f of b minus f of a. The thing about this is that it doesn't matter if this is going to be positive negative or negative positive, does not matter, right? You can just get the m value in there. And so what will happen is, let's just put in these values. Here we go. You will have in here is a times f of b minus b times f of a. And what I will do is that I will follow, right, that value of f and f, right? What I will do now is f9 minus d9, right? There you go. Now you have somewhat of a smarter version of where this is going to land. And what we will do is now we will drag this down in here, and note that your range did not change. Wait lang, hold on. Then D10. Oh, it's getting shorter, but why is the range in here? Oh, I'm just doing E25 and C25. Wait a second. I'm looking at XU. So in this case now, I suppose what we're supposed to do is we're supposed to get the difference between the ranges. Okay. So we will insert, oops, we will insert a row in here. This is now your epsilon r, right? What we will now do is the changes within your xm. Okay. Well, there's nothing here yet. Let's not have your epsilon here. This minus, oops, absolute value of this minus this divided by nu. There you go. That's already great. Already quite great. And then what we will see in here is that your epsilon, right, your approximate value stops at iteration 10, which is much better, right? Which is much better. There you go. And let's say we copy this for your in what do you call this? Let's copy this. Have regular falsy, another formula in here, and what we will have is the x of m. Let's change that now. There you go. What we will have is a times f of b minus b times f of a, and f9 and then d9. Okay, there you go. Let's drag this down. And let's see in here what kind of epsilon we're going to create. Epsilon r. Let's try this. Absolute value of this minus this all over this. There you go. Let's look at our epsilon now. And it stops at iteration 10. Wow. Great, there you go. So we have just seen how the regular falsy method, because it now accounts for the values, right? For the values of the results, not only just the x coordinates themselves, or because it now accounts for those things, well, you have a resulting smarter kind of equation. Let's try this again. Let's try x cubed minus x minus 1. Let's just let's just understand what's happening in here, right? Or you know what? Let's just go back to the original one. There you go. What we will do in here is that we will create a point between these two values right here. So we will have is maybe is this a equals 1 or L na lang, L 1, and then u equals 3. Suppose. Yeah, maybe. And then what we will do is we will have m. M, which is going to be L times f of u minus u times f of L all over f of u minus f of, there you go, that's your new value. And let's try and create the line in here. Is equal to, is this fu minus fl all over u l times x minus u. So that is the thing it creates, and notice that the point is now here, 1.40165. Okay, let's look at the true power of your let's look at the true power of your regular falsy. Okay. Let's have this line, and note that the line is now here, right? So 1.40165. 1.40165. 01. Okay, we go here, and now we will replace our L with 1.40165. Note that what is going to happen now is that it's going to inch closer and closer to this value 1.895. Now the next value is 678,679. You know what? Let's just do this. L and U. 1.67, ano yun? 1.678679. 1.678679. Now we have this, and now it gets closer and closer. 813,844 now. 813,844. And it gets closer and closer. Now you see there's a kind of a smartness that happens to this formula, right? It doesn't just indiscriminately go from here to here, here to here, so on and so forth, right? It doesn't jump back and forth as with our midpoint, or midpoint method or bisection method, right? Look at the values of your fxm. Sometimes it's positive, sometimes it's negative, right? But in the regular falsy method, if it starts as being negative, it will continue being negative until it will until it goes and converges on our value, right? So those are your two bracketing methods, right? And you might say to yourself, okay, the inherent disadvantage of a bracketing method is that you need to find the bracket, right? The bigger the bracket is, especially for the bisection method, the longer it will take for you to do the iteration, right? So that's a little bit of a bummer, right? The next two methods that I will teach, right, that I will introduce are what we call open methods. And in those cases, well, the inherent advantage is that you just have a point and then you can go, right? The disadvantage of those things, though, is that you're not sure if you're going to arrive here at your answer at all, right? So we'll see, right, how those things are going to go. But for now, if you guys have any questions, please let me know, right, as quickly as you can. We will proceed to the second part of this topic in the next video. Thank you.